Swayam Prabha. Digital India. Educated India.
In this lecture, we are going to start a new topic, electrophoresis. Now, scientists in area of biotechnology spend a lot of time, like biochemists and biophysicists, in separation and identification of biomolecules, particularly say proteins and nucleic acids, and they need to analyze, they need to identify and separate these molecules for different purpose, like say know the function, their physiological and biochemical function of these molecules. Now, there are a lot of different properties which are exploited for say identification and separation of these biomolecules. For example, if you can recall, we were discussing about say ion exchange chromatography or affinity chromatography or gel filtration chromatography, where the properties of charge or affinity or size were utilized. So, there are a lot of different, like charge as a property or charge on the biomolecule can be utilized for separation of these analytes in different techniques. For example, ion exchange utilizes charge for separation, mass spectrometry analysis utilizes charge for analysis of biomolecules, and likewise electrophoresis is another very widely used and it is a routine technique which utilizes charge for separation. So, electrophoresis is a separation technique that is based on the mobility of charged particle under the influence of an electric field. Now, a particular biomolecule could carry either net positive charge or net negative charge. So, positively charged particle will migrate towards a negative electrode and negatively charged particle will migrate towards a positive electrode. So, particles have different migration rates depending on their total charge and also on size and shape of the particular molecule to be separated. So, more is the charge either positive or negative, the migration rate will differ accordingly. As well as if size and shape will also affect the mobility in the electric field, because the resistance or the friction which is there in a particular medium will be according to the size and shape of the molecule. So, many important biological molecules, as you know, carry charge, like for example, amino acids, peptides, proteins, nucleotides and nucleic acids, they possess particular charge and they possess ionizable groups. Now, at any given pH, they will exist as electrically charged species, which could be either as cations or anions according to the pH they are in. So, there is one called isoelectric point or Pi value, and at which the net charge is 0, but if pH is below the Pi, then the molecule will carry positive charge, and if it is above, it will carry negative charge in general. Now, under the influence of an electric field, these charged particles will migrate either to cathode or to anode depending on the nature of their net charge. If you see the development of electrophoresis, it began with the work of Tiselius, that is Arndt Tiselius in 1930s, and then from then on new separation processes and chemical analysis techniques based on this electrophoresis are continued to develop here even today in 21st century. Now, Tiselius with support from Rockefeller Foundation developed the Tessal's apparatus for moving boundary electrophoresis, which was described in 1937 in a very well known paper, which is a new apparatus for electrophoretic analysis of colloidal mixtures. So, it started long back, this technique of electrophoresis. By the 60s, that is 1960s, sophisticated gel electrophoresis methods made it possible to separate many biological molecules based on minute physical and chemical differences like charge, size, shape, etc. And this particular development gave a boost to the rise of molecular biology. Like molecular biology was quite benefited, and it came up as a science because of the analytical power which was provided by the technique of electrophoresis. Acrylamide gels and denaturing agents like STS were introduced, and it enabled the separation and analysis of one of the macromolecules, that is protein molecules. In 1970, Lamelli separated components of T4 phase using stacking gel and STS as a detergent. Then the development of two-dimensional gels and isoelectric focusing happened around 1975, and then sequencing gels were developed in around 77. Also later agarose gels were introduced here. So, a lot of development took place in those times. In 1980s, pulsed field gel electrophoresis was developed in 83, which enabled the separation of very large DNA molecules, and also the technique of capillary electrophoresis was developed at the same time. And so, a lot of new techniques are still being developed, which are benefiting in different ways. All right, as we go into the details of this technique, let us first little bit understand the general principle, and let me give you an overview of this technique and what we are going to discuss in this section. So, let me bring you to the screen. All right. So, now let us first little bit understand before we go into details about the electrophoresis technique. So, what we were saying is that a charged species under the influence of an applied electric field moves to the respective electrodes. So, if I say that there is a charged species, say the charged species we just denote it by Q, and this charged species, which could be any molecule, which could be say protein molecule or DNA molecule. Now, as you apply, and there are two electrodes, it is kept in under two electrodes, which is, if we say there are two electrodes here, positively charged electrode on one side and negatively charged electrode on another side. Now, as you applied the electric field, there will be a particular force will be applied onto the charged molecule, so current will flow, and this charged molecule will also move in a particular direction. So, if I say if it is positively charged, then it will move in towards negatively charged electrode. If it is negatively charged, then it will move towards positively charged electrode. Now, earlier when these electrophoresis started with the work of Tessal's, it was mostly done in free solutions. So, there was a lot of problems of diffusion and other things. So, we will come into that a little later. So, as this charged molecule moves, it experiences a particular force, and this force could be given by the electric field that is applied and the charge. So, E q, E if I say applied electric field and q is the charge. So, force which is being experienced by the charged particle under the influence of the electric field is E q. Now, there is another force when a particle moves, like we were talking about size and shape here, that is frictional force. That frictional force will oppose the motion of the particle as it moves through a particular medium, and that force is, you can also call it a viscous drag, and which is can be denoted as F. So, the velocity, if I say velocity of the particle which like at the which kind of moves in under the influence of electric field will be given by E q by F, that is frictional force, or we can also say it is V F equals E q, that is viscous drag after certain period of time, the force which is forward moving force E q equals the viscous drag which is depends on the velocity of the molecules, that is V f. There is another term used which is more popular term is electrophoretic mobility, and this electrophoretic mobility is given by velocity per unit field, or you can say that is q upon frictional force. So, that is the electrophoretic mobility which is more commonly used. The important part, like as I said, let us take an overview here. Most of these experiments started in free solutions, and the separations were done maybe free solutions and then paper and other mediums. And in free solutions there were a lot of problems about say diffusion, convective currents and all those things. So, the separations were not as good, and later on gel electrophoresis where agarose and polyacrylamide gels were utilized. Now, these gels were quite handy in a sense that first the separations were much better due to the sieving effects, there was less of diffusion. So, the band were diffusion limit effects were minimized, the heating effects were minimized where convection currents are concerned, and lot of other improvements took place which could give a very better separation of proteins and nucleic acids in particular. Lot of techniques developed afterwards, like I said in the as we were discussing the history of the electrophoresis, that acrylamide gels were introduced, and then later on agarose gels for nucleic acids were introduced. Remember nucleic acids, agarose nucleic acids are large molecules, and it was difficult to run them on larger molecules of DNA, large size of DNA molecules were difficult to run on polyacrylamide gels, as the pore size in acrylamide gels is smaller. So, agarose gels were quite handy in that. Proteins were run on polyacrylamide gels and not agarose gels, because the pore size in agarose gels is too large to separate the protein. Later on lot of different techniques were developed, as we will discuss. There was like continuous buffer system, there is a discontinuous buffer system, like Lamelli introduced discontinuous buffer system with stacking and separating gel in STS page electrophoresis. Then there were a lot of techniques for DNA sequencing which is not now it is not utilized, but earlier polyacrylamide gels were utilized for separation of for sequencing the DNA, and remember polyacrylamide can run only smaller fragments of DNA. Later isoelectric focusing which was based on the PI values were developed. There was pulsed field gel electrophoresis for separation of very large, like say 60 kb or large DNA molecules were introduced, and likewise capillary electrophoresis and other techniques were introduced, as we will be discussing them as we go along. All right. So, let us come back to our discussion here, and so what we are discussing about, like I gave you the overview of this in a very short about electrophoresis. Now, general principle, as I was discussing, that there is a force and which is experienced by particular analyte or charged species. So, the electrophoresis as such is the migration of charged analyte under the influence of an externally applied electric field, and as we said positively charged species moves to the cathode and negatively charged species will move to the anode. So, the efficiency of this electrophoretic separation as we will be discussing will depend or will be affected by three factors, mainly three factors, there might be other factors also. One is electrophoretic mobility of particular charged species. Another important factor which we are going to discuss is the heating, which is called Joule or ohmic or resistive heating, and which also affects the electrophoretic separation. And then electroosmotic flow, which is kind of quite suppressed in gel electrophoresis, but it could be a problem in say electrophoresis where the medium or say capillaries, glass capillaries or other mediums might carry charges by themselves and can interfere in the electrophoresis run. So, this is like in a support media so electrophoresis can be performed. So, these are three factors, and then electrophoresis like I said can be performed in free solutions or in support medium, which is gel electrophoresis we are going to discuss, and this can act as anti-convective and sieving medium actually these support medium. And gel electrophoresis is the most popular form of electrophoresis and routinely used in different research and teaching laboratories. It is a very important tool in the labs which are working on proteins and nucleic acids, and they are routinely used for different applications. All right. So, let us get into little bit of basic concept or basic principle of electrophoresis and little bit overview I have given. So, what happens is when a potential difference is applied across the electrodes, what it does is it generates a potential gradient which could be given by E, which is the applied voltage actually divided by the distance between the electrodes. So, this potential gradient is the applied voltage divided by the distance between the electrodes, that is E equals V upon D, the voltage upon distance between the electrodes. Now, when the potential gradient is applied, the force on a molecule, that is a charged species which we can say contains a q coulombs of charge, q coulombs of charge is EQ newtons, and this force drives the charged molecules towards an electrode. So, this is a particular force which will be experienced by the charged species. Now, when it moves through the medium, however, there will be also another force which is the resistive force or frictional resistance, and this frictional resistance will retard the movement of this charged molecule. Now, in free solution, the frictional force is linearly proportional to the velocity of the charged analyte, and the magnitude of viscous drag that occurs is Fb or frictional force into the velocity of the charged particle. Now, the frictional force is a measure of hydrodynamic size and shape of the molecule, then the pore size of the medium where electrophoresis is being performed or taking place, and the viscosity of the buffer. So, therefore, the viscosity the velocity of the charged molecule in an electric field will be given by V equals EQ upon frictional force or frictional coefficient. So, that is the velocity a particular molecule will experience or will have when it moves through the under the influence of electric field through a particular medium. Now, like I said, the more common term which is utilized for the migration of charged particle is electrophoretic mobility. Now, as the ion moves or accelerates, a frictional force opposes the forward motion. So, in the beginning, as it is a charged particle is put under the influence of electric field, it will move towards the opposite electrode and it accelerates as it moves through the medium, but as it accelerates, a frictional force also comes into existence, and this frictional force will oppose the forward motion of the ion or the charged species. Now, what will happen is that the molecule which is moving will rapidly reach a steady state velocity, which is steady state terminal velocity, when the two opposing forces, that is the force on the charged molecule due to the electric field EQ and the viscous drag or frictional drag Fv becomes equal. So, this has to be understood that at the beginning, as applied field is applied and the field is applied, the charged particle will accelerate through the medium, but soon frictional force catches up, and as soon as the two force, and that happens very quickly, the two forces becomes equal, and then the particle or the charged species moves with a constant velocity, and that is given here, that is of the two forces becomes equal. Now, here this is the electrophoretic mobility here of a charged analyte or a particle is more commonly used term, and this will be defined as the steady state velocity of the analyte per unit field. So, when charged species has acquired a constant velocity, then electrophoretic mobility of that will be defined by the velocity per unit field, or by the another term called the charge upon the frictional force. So, that is the electrophoretic mobility. Now, electrophoretic mobility is the fundamental parameter which determines the efficiency of separation based on charge to size ratio. So, remember this is very important, depending on say a particular charge species, say two analytes might carry the same charge, but different sizes. So, what will happen? The one which will have a bigger size will experience more frictional force and will move slower than the one which is smaller, but carrying the same charge. Likewise, if two analytes, they are of same size, but they carry different charges. So, one carrying more charge will move faster than the one carrying the less charge, but of same size. Likewise, shape will also play a role depending on the shape, like for example, a spherical shape will move faster as compared to elongated shape molecule. Now, change in pH effectively alters the charge on the ions and their electrophoretic mobility. Like I said, most biomolecules will have a pi value, that is isoelectric point. As you move away from the isoelectric point, you will carry the analyte will carry more charge. So, if you are very close, the pH is very close to the pi or at pi, then the net charge carried by the analyte or a molecule is 0, but as it moves either in below the pi or above pi, the charge will increase as the pH is farthest from the pi. So, depending on pH, the analyte will carry a particular charge which could be more or less, and depending on that how much charge is being carried on the a molecule carries, the electrophoretic mobility will be determined. So, pH will certainly affect the electrophoretic mobility. So, different analytes which separate in the electrophoresis due to the differences in electrophoretic mobilities, and that is how they are separated. Like I said, analytes or charge species having similar charge will separate if their molecular size differs or shape differs, and as they will be experience different frictional force actually. So, even the pore size of the medium and other things will also affect, like for example, for some molecules the pore size may be as big that they do not experience any hindrances as compared to another molecules. So, these factors will determine the electrophoretic mobility. So, if we in equation terms, if we summarize this, then you have a force on a molecule which is q e, there is a frictional force which is given by this equation. Viscosity of the medium will play an important role, because it more the viscosity, more will be the friction. Radius of the particle will play. So, electrophoretic migration velocity will be affected by all these factors, and as we said, electrophoretic mobility is force divided by the friction, and this will determine, like as we have already discussed, this is equation gives the electrophoretic mobility of a particular analyte or charge species, and all the factors like viscosity, particle radius, and all these things have been taken into account here. All right. So, one factor was the electrophoretic mobility. Now, another factor which is important in the migration of the charged species or electrophoresis run is the heating, which is called Joule heating or ohmic heating or resistive heating. Now, when the current in the solution between the electrodes is conducted mainly by the buffer ions, a small proportion being conducted by sample ions, then Ohm's law expresses the relationship between the current, voltage and resistance, which is given by this particular equation. Now, the distance migrated by the charged molecule will be proportional to the current flowing and the time. The current can be increased by increasing the applied voltage, and in principle electrophoretic separation could be accelerated. So, certainly when you increase the current or when you increase the voltage, the current will increase, and certainly the force experienced by the molecule will be higher, and so the electrophoretic separation could be accelerated, and the distance migrated will depend on current and the time for which this is being done. But there is one very big problem here, which comes out as you increase the applied voltage and as you observe this whole phenomenon, and that is the generation of heat in here in your electrophoresis apparatus or wherever you are carrying this. So, during electrophoresis, the power generated in the supporting medium will be given by this particular equation, that is W I square R, and the most of the power which is generated here is dissipated as heat. So, what is the problem here because of heat? Now, heating of electrophoretic medium or apparatus has lot of effects, actually several effects which are important here. Now, what will happen when heating is done or this apparatus or the medium is heated? One is that an increased rate of diffusion of sample and buffer ions will occur as heating is increased, and which will lead to the peak broadening of the separated analytes. So, as the heat increase take place, as the current is increased or whatever means, and as the time goes by on an electrophoretic apparatus, this will certainly lead to the diffusion of the sample, and therefore, the resolution or you can say peak broadening will take place, and the separation will not be ideal or will not be good. So, this is one major problem. Then due to temperature rise, there will be temperature gradients may be formed, and the formation of convection currents leading to the mixing of separate samples would occur. That is another problem due to convection currents, and this is quite suppressed, like I said. If you compare free solutions to the gel, the gels there will be less a problem of convection current. Then there is thermal instability of analytes. Now, many analytes which are of biological origin are sensitive to heating. As the temperature rise, it may be like if you do not want to denature of your enzymes or proteins, but at higher temperature certainly these many of these enzymes and proteins will denature. So, that is another problem, that if you want them in native form, then and if there is a heat generation, then certainly thermal instability will be a big problem for analysis of these samples. Then there will be a decrease in viscosity of buffer as the temperature rises or heat is generated, and as the viscosity decreases, there will be a reduction in the resistance of the medium. So, there are certain like these several effects which will certainly occur when heating occurs, and they will affect the electrophoresis run. Now, there are methods for decreasing this heating. So, when electrophoresis is being performed, it could be performed at constant power rather than constant voltage, where current increases and therefore, heat output is increased. Now, running a particular electrophoresis on constant power can eliminate not the heating, but the fluctuations in heating. So, even when you run it at a constant power, there will be generation of heat, that is constant heat generation will take place, and still it will be a problem. So, how to solve this? One is that you can do is you can run the electrophoresis at very low power or a current or applied voltage, but there what will happen, you will certainly increase the analysis time. So, when you do it at lower power or low current or low applied voltage, the analysis times will increase, and this will result certainly in poor separations. So, then again this does not solve the problem. So, what has to be done? A balance in reasonable power setting for appropriate separation times needs to be used. So, you have to somehow work out a reasonable power setting and what analysis times, so that right analysis times could be obtained for separation and your resolution does not go down. Then what you can do is, another method could be to dissipate heat by cooling apparatus or cooling system. So, if cooling systems could be employed where chilled water could be circulated, or in cold room you can run this to remove the liberated heat. And another thing could be done is to dissipate heat is thin gel or small diameter capillaries which have large surface to volume ratio can be used, and their electrical resistance is high, thus current flow is reduced for a given voltage. Now, problem with all, though these are good solutions, but for say problem with even doing in say like small diameter capillaries or say slab gel, many times you can control the things at the center, but at the edges there might be differences in the heat, because heat is being dissipated at the edges and not at the center. So, there will be certain convection currents or diffusion things might occur, or the charge species, different species might not experience same force, and due to the heating there might be a problem. So, there will be certain problems which needs to be solved, but certainly you can reduce them by these measures. So, the two factors which we have discussed is electrophoretic mobility for successful electrophoresis run, and another was the heating problem, and this could be solved by balancing the power supply or power like power setting and analysis times. Now, third important factor which affects your electrophoresis run is that is electro-osmotic flow or electroendoosmosis, EOF which we call it. Now, electroendoosmotic osmosis or electroosmotic flow refers to migration of the bulk liquid towards the cathode, and the phenomenon happens because of formation of double layer at the wall of the capillary. How does it happen? What happens is it occurs due to the presence of charged groups on the surface of the support medium. For example, paper will carry say carboxyl group, glass and silica, fused silica will carry silanol groups, agarose carries, if it is not too purified, sulphate groups, and likewise these surface charges will certainly disrupt the normal electrophoretic flow actually. So, the phenomenon is quite well explained in case of capillary tubes. Now, in fused silica capillary tube, the silanol groups are deprotonated, or you can say they are ionized at pH higher than 3, and these ionized silanol groups create an electrical double layer at the capillary wall or the capillary wall electrolyte interface. Now, what will happen? Positive ions in solution will migrate to the wall, and a double layer is developed at the wall of the capillary. Let me show you this on screen actually. You have a capillary which could be fused silica or other capillaries. Now, like I said, above pH 3 these silanol groups are ionized and they carry a net negative charge. And of course, as you increase the pH, these groups will be charged, more groups will be charged, maybe at pH 3 or say there is certain less number of groups charged or not complete charge pattern has taken place, but what is going to happen is as you increase the pH, many more groups will be charged. Now, so what you have at the surface, inner surface of the capillary wall, you have negative charge. Now, there is a particular electrolyte in the capillary, like if you say it is a free solution you are utilizing here, then they will, that particular electrolyte or particular solution which is inside this capillary will carry both positive and negative charge. Now, what will happen? This positive charge will be attracted towards the negative charge here. So, what you are going to see is on both sides of the wall, that is inner side of the wall, you have a layer being created which is we call a double layer of negative and positive charge. On both sides you have, so both these positively charged ions from the electrolyte or from the solutions are moving towards negatively charged particles. Now, these are positively charged, then there is another positively charged and negatively charged ions which are here in between actually. So, these are in between here. Now, what happens is these negatively charged will be aligning here, and when the voltage is applied, then these positively charged ions will move towards the cathode or negatively charged electrodes. So, when these which are attaching to the wall, when they are applied, the voltage is applied, they all move towards, and some positive charge here, they will move towards the cathode. Now, essentially what should happen? The positively charged ions should move towards negatively charged electrode, and negatively charged ions like these ones should move towards the positively charged electrode. But because of this formation of double layer and their interactions, the whole flow, electrolytic flow occurs towards the cathode, and this flow kind of carries the everything with it towards cathode. So, that is the electroosmotic flow, and which will occur only when there in like these support media or in capillaries there is charges, like I said there could be on agarose, there could be on paper or say acrylamide, this could be done. So, now what is happening is that positive ions in solution migrate to the wall, and a double layer as we have shown you is developed at the wall of the capillary. Now, there is a stern layer which is layer of positive charge that compensates for the negative charge on the surface, as I have shown you on the capillary inner capillary wall, and there is a diffuse layer which is adjacent to that the stern layer, which is mobile actually, which could be mobile cations actually. So, what happens when potential difference is established or applied? The cations, like all positive charge will in the electrolyte near the capillary wall will migrate towards the cathode, and what they will do is as they migrate towards the cathode, and due to all these interactions they will pull whole electrolyte solution with them towards the cathode, creating a net electroosmotic flow towards the cathode. So, here you have a particular situation where electroosmotic flow kind of dominates, and even when this negatively charged species might be trying to go towards other side, but they are not able because of this electroosmotic flow. So, this figure kind of explains what I have already explained, that there are fused silica capillary here with negative charges, and I said, as I said at different pH they will be charged differently. There is a stern layer here which is shown here, that which is like the cations compensating for negative charge on capillary wall, and there is a diffuse layer which is here, and as the applied voltage is applied, everything moves towards cathode. So, that is a phenomenon which is called electroosmotic flow. Now, so what is happening is dragging the bulk of solvent towards cathode, and these are the equations here for electroosmotic flow, which is dielectric constant, that is zeta potential, the applied electric field, and so these things which are here kind of, and viscosity gives you around what will be the electrophoretic mobility of electroosmotic flow, and that is the velocity in electroosmotic flow by E, that is applied electric field. So, electroosmotic flow is, like I said, suppressed in gel electrophoresis and other, but it is quite utilized in capillary electrophoresis, as we will discuss in later classes. So, as we will be discussing in subsequent lectures here. Now, electroosmotic flow is in opposite direction to analyte, that is electrophoretic flow in general, one that then electroosmotic flow is practically equal across the capillary, and so the band broadening is minimal here. Then electroosmotic flow, they are not reproducible. So, many times separation efficiencies are low, and since they are irreproducible, and so you cannot really rely on them if you are trying to do it again and again. So, in gel electrophoresis, this thing is quite suppressed and it is not existed, but in capillary electrophoresis it is being used for separation. And this shows here how does electroosmotic flow, the front will look like as compared to HPLC flow or other flows. Now, when you have electroosmotic flow, what is the movement of the charged species under this influence actually? So, if you see in this figure here, the velocity of electroosmotic flow, like how does these charged species move, and if you can see here, there is a comparison here that if you have a positive charge, then they will, like if you can see here, there is one flow towards this, that positively charged, more is the positive charge, more rapidly it will move towards the cathode, less is like charge it will move. So, relative, it is a relative movement or migration depending on the charge being carried by the species. Likewise, neutral species will somehow will just move through, but not as rapidly as the positively charged species. Then negatively charged species, though it is will experience electroosmotic flow, but it will move towards other side, that is towards anode, and upon depending on how much charge it carries. So, what is the net flow here? Net flow is that the positively charged species in electroosmotic flow will move much faster or at highest rate, then followed by another positively charged species, but carries less of the positive charge, then it will be followed by neutral, then negatively charged species, and then less more negative charge. So, less negative charge will follow the neutral and more negative charge will resist the electroosmotic flow, but still it will move towards the cathode only with the bulk solvent, that is the drag of the bulk solvent. All right. So, these were the three important factors which which are very important for electrophoretic run, and these are quite like, say for example, Joule heating, or there are a lot of things have been done to improve the electrophoresis run to control these, like say electroosmotic flow is totally non-existent in gel electrophoresis. Likewise, Joule heating could be suppressed by cooling systems and other means, like you can run chilled water through the plates where the where this particular heat is being generated, and electrophoretic mobility likewise could be improved by taking corrective measures. Now, in this lecture, we to summarize this lecture here, what we have done is we have taken we have discussed about the electrophoresis, basic concepts in terms of general principle of electrophoresis, where we have seen how a charged species moves through a medium when it is under two electrodes, and when applied field, the field is applied, actually a voltage is applied. There are three factors which are important, that is electrophoretic mobility, Joule heating, and the electroosmotic flow. Now, like I said, electroosmotic flow is only like applicable in certain like say capillary electrophoresis or other, if say certain medium is not pure, then that will certainly affect the electrophoretic movement. So, these are factors which are important. In the next lecture, we are going to discuss about the basic components of electrophoretic system. Just to introduce a bit, basic components which will include say electrophoresis apparatus, the place where you will be, and we are going to discuss mostly about gel electrophoresis. So, what is the matrix is being used here, gel apparatus where gel is being cast, how to load the samples. There are different matrices like agarose and polyacrylamide matrices, which are run on one. Agarose is run mostly on horizontal apparatus, and acrylamide gels are run on vertical apparatus. Then there are like lot of factors, say you require a power supply apparatus, and how these gels are cast, how these whole process of electrophoresis is conducted. We are going to discuss that in the next lecture, and likewise then we will be discussing different techniques like discontinuous buffer systems or continuous buffer systems, how proteins and nucleic acids are separated on different gel systems, and what are different variations of electrophoresis technique. Like for example, we were discussing about isoelectric focusing or capillary electrophoresis or STS page electrophoresis, and what are their applications and utility in in various research labs and in identification and analysis of various components or various biomolecules. Thank you.